Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. Today we're going to be discussing and getting into a little bit more details of the Common Lisp type system. Past weeks we were, and prior to our short break, we're covering a couple of data structure libraries, particularly functional data structure libraries, in the sense of FSET and Sycamore. And there are many other data structure libraries, as probably many of you have already seen if you either look out and go to Google and search through the Google search results, or go to Cody Reichardt's nice little curated awesome CL libraries. One of the libraries that kind of provides this data structures and algorithms is the Lisp interface library, which implements a particular design style called interface passing style. In order for us to cover this, I thought it would probably be easier first to cover the Common Lisp type system itself and how you can actually leverage it to your advantage. In the past, we've actually covered bits and pieces of this, so some of this might be review, some of this will be new, but I thought it would be better to actually cover it all in one go, so to speak. As usual, if folks have any questions at all, please don't hesitate to post in the chat window on the live chat, or if you're on the Hangout, post your questions on the Hangout as well. Just give me just 1 second here so I could monitor something and go to here. Okay. This. Good. All right. Let's begin. In the past, we've covered bits and pieces of this of the Common Lisp type system, but I thought today we would, like I said, would cover it in a little bit more of a deep dive. Common Lisp, as many of you know, has a fairly flexible type system, something that you can use to inspect, check, manipulate types. You could leverage this both as a form of runtime type checking as well as compile time type checking. You can use it also because it's integrated into the runtime system as well as the REPL. Use it as a way of providing warning messages to your users of your APIs, as well as provide particular errors to prevent certain types of errors from occurring from the use of your particular libraries. And or if you're writing an application, you can also certainly use them to speed up code and get some performance improvements. But in order to understand and how to leverage this, we're going to have to first start talking about, what is a type, what is typed in Common Lisp itself, because that's something that is slightly different than other programming languages. Okay, Common Lisp and Lisps in general treat values, that is, what is actually set up. So if we have, say a parameter test variable, okay. In fact, I'll use def_var in this case so I can actually not have to provide an initial value. If we have a variable in this case, and this is currently in the global scope because it is using a def_var or def parameter, but it certainly applies to as well things that are created in the let form. When you compile this, what you're actually doing is you're creating a placeholder for a particular object, and it is that object that will have a particular type. Okay, so this is very different from statically compiled languages, where at the point of assignment, you are declaring the type in the type systems. So just sorry to stop here, but there's a question. Are you just covering the basics? No, I'm going to try and dig into not just some of the basics on creating custom types, but also some of the type checking functions as well. We will cover as well also check type, the declarations when you're defining functions, as well as we'll cover, there was a question on the YouTube stream regarding what we're covering specifically. We're also going to be covering just some of the type case statements, because that's a particularly interesting thing that I've figured out the other day, which I thought was pretty cool. But let's continue on. So like I was saying, the variables that are being created, again, either using def var, def parameter, or if you're defining it in let form, they're again just placeholders for objects that have types. Okay. When you're setting f this type here, that means when you set f, this variable, okay, and you provide it, say, a variable, a value, in this case 1, 2, 3, 4, that value is what actually has a type. So when you use, say, type of, okay, which allows you to look in and introspect and figure out what type a particular type is for our variable, this, of course, I have to remember to print because we're in a script. We're not actually doing this at the REPL. Hold on, let me just do this. Okay. For folks who are watching on the YouTube stream, please let me know if the font sizes needs to get bigger or not, just so that I can adjust it for folks who are watching the stream. It looks kind of good to me right now, but I could certainly make it bigger too as well. That might be. See if that works. Okay. So when we print this type of, for some reason it's not printing. Let's see. Let's do this. Type of. The value that's actually returned by the REPL, the type of, is the return value, that is actually the type of the value object that was assigned to the variable. So do not think that this variable is now set up to being of this type. And this burns a lot of beginner Lispers when they're starting to get into Common Lisp, and especially when they're getting into the type system Common Lisp. Common Lisp is a dynamically typed language. We can actually set this guy to being anything right now. Even though right now this is an integer, we can certainly do this. And now type variable is a simple character array of 5. So the values have actually a type, not the variables themselves. The variables, you could think of them as pointers to particular objects that are going to be in memory. And they may be different. They may assign to being different objects in memory. They're not going to be trampling over each other. If you actually look at the Common Lisp hyperspec, specifically section 4, which it describes some of the basics of this, in the introduction itself, it goes as far as saying that types themselves, which are representing a set of objects, which is a set of values that are going to be assigned to a variable, they are never actually explicitly represented as objects themselves in Common Lisp. Instead, you provide what are called type specifiers. And there are a list of type specifiers. There are a huge bunch of them. Section 4.2.3 of the Common Lisp hyperspec actually talks about most of the, I think, built-in ones. Actually, it was, let me take that back. I think it was in section 4.2, section 4.2.3 actually has the type specifiers that are already built in. These are all built-in types that are available for you to use. And again, we'll later on I'll provide some examples on where these can go, how you can use them, and so forth. So one second, I had another question here. I'll mention for folks who are on the chat at the end. I'll give you my handle on Discord, so you can actually ping me if you have any questions. I usually try to keep it at the end, so that way folks can actually go through and watch the material and provide some feedback on that. Okay, so as I was saying, values have types, variables do not have types, variables are objects. What exactly does Lisp provide in terms of built-in types? We talked about a little bit of this in earlier things when we were talking through, especially in the Practical Common Lisp book. We were introduced to some of this stuff. But Common Lisp does have an actual type hierarchy. Most of all built-in types, I think all built-in types actually, are essentially all inheriting from a type hierarchy where the root of the type hierarchy is T. And yes, that is the letter T. That's actually an atom, if you actually go and actually look at it up. And you have built-in types as well as essentially in order to hook in to hook in the object system into the rest of the type system. As you recall, the built-in top level standard class and standard, I think actually it's not standard class, it's standard object that is actually inherited from T. And you can obviously look up the class precedence list again, going back to a little bit of our, if we use the meta object classes, you can actually look up the class precedent list for a particular type just to see how its inherited structure is created. That's on the Common Lisp object side, as well as technically all the built-in types you can look up the class precedence list too as well. One second here. I have lost my notes. Okay. So there being a type hierarchy, you can actually use some facilities inside the Common Lisp REPL to actually go and look up learn more about some of the types. So like if you use describe and you look up the type integer, you will see here some very nice information on what it is. It tells you that it names a particular type, which is a built-in class. A lot of the Common Lisp built-in types were converted into objects. There are some that have there's some type information that's used behind the scenes in a lot of Lisp implementations to make sure that if they're mapping to particular machine representations, they could certainly do so. This helps with some of the efficiency guarantees that are provided by the Common Lisp compiler. But in general, you do have this upcasting hierarchy for a given type. So in this case, if we're looking at the class precedence list of, say, integer, you can look at the fact that you have integer being a part of the rational numbers, which is also part of the real numbers, which is also part of the numbers in T. So you can read that left to right as being from most specific to least specific. Again, this is probably review for a lot of folks who have been following along with some of our talks, but I'm just kind of bringing it in. Additionally, you can see how it lists more specific types from itself. So in this case, fixed num and big num are both subclasses and more specific types of the type hierarchy. So with this information, you have two functions that you can actually leverage. you can actually leverage the function type p, okay, to determine if something is of a particular type. So in this case, if I say type p is of a type integer, it will go ahead and do that. You can also see how this can work with all the base class types as well. If we say if it's of a float, it will say that it's of a differing type. It was nil. This gives you the ability to actually go in and look up in the hierarchy whether or not something is of a particular type. And later on, we'll see you could write certain types of functions that leverages this pattern. Now, I'm briefly mentioning it just merely because of the fact that a lot of folks would argue that that this may not be a good approach to actually just keep on heavily using the type system, type information in the cases that I'm mentioning to actually write your code that way, because there could be cases where you're going to have some duplication. But in recent languages, say for example like Golang, some of these type switches and types assertions have become at least a common pattern for those languages.
Hello.
Oh, hi Michael.
How are you doing?
Pretty good.
I'm sorry to interrupt.
No, there's no problem. So, type assertions and type switches are certainly something that that other languages have started adopting. Whether or not that you should write APIs leveraging this technique, I don't think it's necessarily a good idea, but I'm going to mention it here because there is code out there that you should actually understand what is it doing and actually be able to use. And also, once we understand how the type system works, we can start getting into the Lisp interface library, because it uses some of these techniques to implement ad hoc polymorphism.
We're covering types today.
Yes, we are.
Interesting. One quick note, at the top of your buffer there, you're printing the type of some variable.
Yes. That does not work, by the way.
Okay. I just wanted to point this out to people following along at home or whatever. Type of is a function standard in Common Lisp. However, it should only be used basically at the REPL. You should never use that in code. With like some very, there's some restrictions to that rule, but the reason why is because implementations aren't required to return the same thing as other implementations. For example, if you do type of on a string, there's like 7 different answers you could get back depending on what implementation you're using. So don't do any logic-based programming based on type of. Just use it for quick tests in the REPL and whatnot. Right. Now, obviously, if you use it on a class, all classes have a type of the same name of the class. So that's the only exception I can think of. But still, you could just do, class name, class of. Right. Instead, that's a little more explicit and gives better intent. But type of is basically unportable to use.
That's actually a very good response, because I was wondering about that. I was going to go look up in the hyperspec, but I just kind of just switched over. I was like, you know what, this works in the REPL. I'll just use it in the REPL. But that makes sense. I didn't realize that different implementations could implement the return value a different way for type of. That's very useful. Actually, the hyperspec doesn't actually specify that in the section though, so I didn't realize.
It's at the very bottom of the hyperspec page for type of. It's in the notes. It says implementations are encouraged to do something, but they're not required to. So.
Excellent. Good to know.
From what I recall, anyway.
So, one more predicate function that most people should be aware of, because we covered type P, is also subtype P. Now, I don't know in what situation you would want to use subtype P versus type P. I mean, maybe if you're writing a bit more of a complex, type introspective API, it might be useful. But I'm just going to mention it here because it is yet another thing that you can use. Subtype P basically checks to see if your types are subtypes of each other. If type 1 specifically is a subtype of type 2. So if we say, in our case here, is integer a subtype of a rational, you should get true. Now, the return value of subtype P is multiple return values. The first one is, what was it again? Whether or not it is a recognizable subtype. And the second return value is how certain it is that the subtype 1 is a if type 1 is a subtype of type 2. So you should interpret this as type 1. The first return value is yes, type 1 is a subtype of type 2, and if the second return value is true, it's an accurate depiction, which means they actually looked up probably in like the class precedence list, found the two being of subtypes of each other, and were able to say for absolute certain that type 1 is definitely a subtype of type 2. All right. Now, there is some cases where it might provide you a false that it could not, and a false, meaning that subtype P could not determine the type relationship between the two types. But that will certainly happen only in cases where it can't actually use, like, say, the introspective analysis of like the class precedence list to determine whether or not.
Yeah, I think that's like I get confused about that all the time. Like, I don't use subtype P that much.
Yeah.
But I gather that the reason why is because, well, right here you're only using atomic type specifiers,
right,
which are just symbols. But like you could write a type for like all integers between 1 and 10 or whatever, and then trying to compare that with something else to see if it's up. Like, you can get arbitrarily complex with types, like with satisfies to do like runtime type predicates and stuff like that. So
right,
and there's only so much it can do at compile time anyway. So
that's actually a very good point, because it's going to be extremely. I could certainly see subtype P getting messed up if your satisfies is a very complex predicate. For folks who are unfamiliar with what satisfies is, we will be talking about that when we start talking about def type later on. I just wanted to cover some of the basics right now that allows you to go and interact with already the built-in types, some of which are very useful, some of which will help improve performance of certain programs if you add them in. But I'm going to say up front, don't think that just adding types to your functions is going to help improve the performance, the guaranteed performance. You're going to have to do some profiling to figure out where type annotation should go. That's something that I've been slowly figuring out as I've been, writing more and more Common Lisp code. I thought you could just simply say, okay, add declare, which we'll be talking about a little bit, and specifying the types of these arguments, but that certainly doesn't.
That's complex.
Yeah.
That's a whole other topic, I think, because for one, implementations aren't even required to honor anything in declare except for not inline and special. So nothing to do with types. Like,
right.
Implementations can totally ignore all of that.
Right.
And like other implementations won't even make use of types unless you bump the speed up or something like that. Like SBCL does very advanced type checking when speed is 3 and you have the types declared. But implementations don't have to do any of that. So.
Right, and I think that's if there's a lesson, or if something that you guys want to take away from this, at the end of the day, although this type system is here and it's at your disposal, and it gives you the ability to get certain things and certain benefits, it's really up to the Lisp implementation as to whether or not it will honor certain some of these and actually expose them as features.
But I will say, if like the viewers at home really value like statically typed languages, where the compiler can deduce a lot of stuff at compile time and give you like like Rust spiral checker where everything happens at compile time or whatever, you can get really far if you use SPCL.
Yes.
Like if you're using compile time constructs like structure objects as opposed to classes. Structure slots let you annotate the types of those slots. So now any function that basically takes an instance of a struct, the compiler can deduce that instance is of type that. So any access for anywhere down the call graph in basically your whole program, it can detect right away. Okay, this type isn't correct. You get a compile time error rather than some like runtime thing where you have like garbage in, garbage out, nils propagating through your call stack, and like the error you get is way too late and stuff like that.
It's so funny you say that because I've been using SPCL almost exclusively now just because of a lot of the advantages that you're speaking of. Like
so you can get really like the type inference of SPCL when you're using like stuff like structs and annotating your types and everything is absolutely incredible. Like, and the performance is really good too. So it's not only the performance, it's the the static analysis aspect of it. Like when you CC on a function, even if that function is far away from like the struct definition or whatever wherever your types are declared, if it can detect that those types, and it usually does, are of some type that was declared elsewhere, like in the struct definition, it's going to error right there when you CC. It's going to let you know that there's a problem. So the type inference of SPCL is really good if you're looking for the performance benefits of like statically typed languages and stuff.
Right. So it also
it's gradual typing, right? Because you can start off without types and add them little by little as you go, and you get the best of both worlds.
Right. I just want to add though that this is the performance aside. I mean, we can both say at least. And this is a comment that actually someone brought up in the YouTube chat, and you're absolutely right. I don't know how to pronounce your handle there, but types are not only about performance. They're at first and foremost about correctness. If you correct inputs going into a function and making sure that they are of the same types will give you some nice guarantees, and being able to check that at the type level will prevent compilation from ever occurring, which I think is really, really useful. But with respect to at least Common Lisp, you get the added benefit because you can argue that Python gives you that kind of same thing. You could give if you add some level of assertions inside of your APIs, and so can Ruby. But what Common Lisp provides you that none of the dynamic languages, well, not none, I would say enough of the current dynamic languages in use do not provide, is this ability to leverage that type information if you declared it at the time, and if your implementation uses it to generate really efficient, really performant machine code. And I think that's something that I cannot stress enough. SPCL especially, I think, is probably the best open source implementation that does this, but that's just my opinion. I've been using SPCL for a very long time. CCL, I've heard, some people say CCL also is compilers rocks too as well, to an extent. But in terms of just type inferencing, you just got to check out some of the stuff that SPCL provides, and it really, really is eye-opening as what it can give you. I think even for an example, and I will illustrate this in a bit. We're gonna go through, like, say, what it can provide in terms of just type inferencing for say a function declaration, and we'll see that when you do describe on a function. But first, there's one more thing that I wanted to talk about, and this is something that Michael, since you're here, I may as well ask if you use this way. So there's a couple of operators that we've used over time, over the course of our different discussions, and some of them can be used to actually go and specify types. One of them we've already seen is the declare function. So if we had this dumb add, we go back to add. I always use add for some reason, and we say that A and B are both fixed nums.
Okay. I don't think your screen is updating. Oh wait, no. Oh, I'm sorry. Yeah, it is on my other computer. I got you pulled up on two computers here. For some reason, my other one froze, so ignore me.
Okay, for a second there, I was like, what? And I'm now just double checking to make sure that it's in the YouTube chat live stream.
Oh, you know what? Never mind. I'm watching YouTube on the other one. I forgot. Okay, so I'll watch the other one that's actually live. Sorry.
Okay. For folks who are in the Hangouts, can you guys see my screen? Just ping me on.
Yes.
Okay, good. All right, excellent. I just want to go through that. All right. So we've used this before. We've declared fixed num types. We've declared a function before on this, and we can go ahead and compile this guy. And if we use, it's not type of. It might be type of. No, I think I can just get it from describe. It will give me the signature.
Way, declare is not a function.
Declare is not a function. That's right. It's a. How can I?
It's just a symbol.
Yeah, it's a symbol.
It's not even a macro.
It's not even a macro. Okay. So it's a hint to the to SBCL, right? Like this, like if you do declare ignore or something like that, right? Because I've used this before.
Well, you can only have one declare form.
Right. Let's say declare ignore something here, right? Right. This is hinting to SBCL to ignore this B, right? It's what's being passed into the compiler when it's parsing that information. Yep. Is my understanding.
Yep.
Okay, so let's go back to this. If we, no, it does not give. Oh, it does. Okay, perfect. So when you describe this function once you've compiled it, okay.
And by the way, you can condense the fixed nums there into a single form. Just go fixed num AB.
Oh, sweet. Okay,
You can have like one list for every type, basically.
Perfect. So let me do that. That simplifies things. Okay, but the signature, this doesn't change anything, right? Yeah, it doesn't change anything. Perfect. You could see that by just declaring it, if we used, I'm actually kind of curious about this. If we use this guy in, let's say, defun add and double. I don't think this is good. I don't know how deep the inferencer works, but we'll try this anyway. If I just say 2 times add AB, okay, and I compile this one. If I describe add and double, no, it does not. So the first time when we declared, and this is something that I wanted to mention to folks.
Well, for one, I would add the optimize speed 3 to add. I'm not sure if SBCL is going to do aggressive optimization without that.
Let's see.
And now it's saying, because both A and B are fixed num, adding two fixed nums together is not going to be a fixed num. So it's basically saying that the result could possibly be a big num.
Okay, so it could overflow, is what you're saying. All right.
Well, I wouldn't use the term overflow because that usually implies wraparound.
Okay,
in
so
other languages, but
right, it's promoting. It's going to automatically promote.
It's possibly promoting it to a big num, which can never be optimized because it's constant.
Got it.
It's not the type that you expect. So in this case, either remove the aggressive speed 3 optimizations or make them both like unsigned byte 16s or something. Basically unsigned byte 60, because SBCL requires 2 tag bits on 64-bit architectures.
So unsigned byte 16, you said?
Basically anything lower than like 61.
Got it. Okay. Let's make these. Let's make these two 16-bit integers just for the sake of this example. I'm just trying to see if how deep the inferencer is going. But let me first discuss this one piece for folks who haven't seen this before. When you compile with SBCL, again, I think there are other. I think CMUCL also does this too as well. I haven't used CMUCL, although if you're going to be using CMUCL, honestly, you may as well use SBCL since SBCL added some improvements from CMUCL. It's I think it was a fork of CMUCL at some point before it became.
Yeah, years ago, they both used the same compiler, which is called Python. Ironically enough.
Right.
The fastest Lisp implementation is called Python.
Oh man, yeah. What's amazing is the fact that when you do a describe on a compiled function, it will give you a function signature type it potentially derived. Now, if there isn't any type information that it could get, it would do what we saw earlier, which is, and if this doesn't work, yeah. If it couldn't figure out the type information, it would provide essentially true saying that the root level, it's not true, sorry, it's TT, saying that any type can go into this particular function. Which could lead to some problems if we end up, for example.
I'm curious what that would say if you mark add as inline.
I don't know.
I'm wondering if the body of add and double would, it would know the types, and I'm wondering if
I do declare inline,
the parameters would be changed.
Add, I think is what it is.
Well, you would.
Hold on, let me go look that up. I have to go and see what
that has to be a declaim. Well, that might work. I'm not sure. I don't really use the declaration much. I use the proclamation, which is declaim as a top level form, like above add.
So there is declaim and there's proclaim, but proclaim I thought was
proclaim is the function. Declaim is the macro.
Okay, got it. So if I wanted to use it at the top level, I would have to go probably here. Proclaim inline.
Well, I don't see a reason to use proclaim. Declaim does the same thing. I don't remember I don't remember what proclaim actually.
I'm gonna look this up here. I have the hyperspec open in another window.
I've never had any reason to use the function over the macro.
So proclaim establishes the establish. So according to the hyperspec, proclaim establishes the declaration in the global environment.
Yep.
You can use it at the function level. So if you use a declare, I don't think you could use a declaim here. You have to use a proclaim here.
Right. That part of the function body only accepts a declaration.
So this inline.
Yeah, that's a function. It's not a macro.
Oh right, sorry. Oh wait, inline is a function?
Proclaim is a function.
Not a macro. Got it. Okay. So I should use declaim here, and it will internally do proclaim. Let's see if that works.
You have to compile it one more time. It's just saying that add was used, so it's actually embedded into the body of add and double already. So it's saying that it's not going to have any effect because add and double has to be recompiled again.
Okay, so let me do this. Add this. So this has to be compiled MCR. Got it. And now...
Well, it's already fixed.
Okay, it's been fixed. Okay.
Okay.
So now
do the describe there for add and double.
And it still doesn't.
No. Yeah.
Okay. Interesting.
Now, if you remove the type declaration from add and put it on add and double, because add is inlined, it's going to receive the type information from add and double.
But add itself will not be.
No. If it's called anywhere outside the context of add and double, it's not going to be optimized, right?
That's right. Okay.
But inlining will give you the optimizations of the calling function.
Oh, hold on 1 second. I messed up my. I am forgetting right now. That's what I was looking for. And this guy. There. Better. And we do this. He said declare. This guy has unsigned byte 16 A and B. So now.
You have to move the speed too.
Okay. Oh, I do.
Because that's not optimized right there. It's gonna cons a big there. Okay, yeah, and I'll put that there.
Optimize speed. Okay. Good. All right. Wait, did I compile this? Yeah, I did. Okay. So let's see this. So now this is add and double. And if we do add, it's not going to do it. But the inline proclamation saying that it's
and now try disassembling add.
Hold on 1 second. Let me just increase my buffer size here. Disassemble. And
Going to be highly generic, yeah. Well, you see that generic comment on the right there?
Yeah,
That's generic. It's not optimized at all. But if you disassemble add and double, it might even be less code than add.
35 bytes, add and double. Let's see. Holy crap!
Yeah.
That's nice.
So there you go.
So
very few instructions there. Starting from the CLC there, that's just the exit from the function there.
That's right.
The return value and stuff.
Right. That's pretty cool. So for folks who are watching this right here alone, and when you're profiling, don't take this as being let's throw types everywhere. No, don't. Figure out where your bottlenecks are, and if you just simply add some type information in there, especially if you know, for example, what the types that should be passed into a particular function, it would be very useful because it provides hints to the compiler to make certain optimizations. Because otherwise,
I would say don't ever inline as you're developing, inlining can, if you inline a lot, aggressively, you're gonna, blow your CPU cache for one. So, you might not get the same performance characteristics on other hardware because your CPU cache is going to be so saturated with all the functions inlined. But for two, it's a real hassle for dynamic programming because you got to remember to go and recompile the calling function, and then every time you change the inline function, you also have to go and recompile anybody that's using the inline function. But usually you can get close to the same performance characteristics just by using types and optimize. If you need to inline, do it later after the fact, but don't do that while you're live coding, trying to sketch an idea out, because it's more hassle than it's worth.
Right.
It's like macros. When you go and change a macro, you gotta go and recompile every function that's using that macro. That's a huge time sink.
Yeah.
and you're not going to get much benefit anyway. In few cases, you'll get a little bit of benefit, but in most cases you won't. It's best to just optimize your functions with types and the optimize speed 3 declaration.
Right. And
only inline if you have to, not during live coding when you're trying to first sketch an idea.
When you're prototyping, do not even consider inlining as being like some sort of like magical thing that you should just do. Just prototype, get the program working, then do some profiles, figure out what particular bottlenecks might benefit from being inlined, and then make those declarations inlined when you're getting ready to at least release something or otherwise. But even there, and I'm going to say this to API developers and people who are writing libraries, please let us know if you're going to do something like that. Just because if we end up using some of your functions as helper functions, and then from one release to another, something gets compiled or changed, and we're using it in a running image, I may not know. But this is just I may not know when something's inlined or not, and if that screws up, the performance of my program, I'll be pretty irritated. Okay.
So one more thing of something you should not do, and I would even say you should not do this in a release setting after you're done coding, is please do not use optimize safetyzero.
Yes.
I have seen so many libraries on ClickList that use that drop me into LDB and just corrupt memory. You gotta be really experienced and know what you're doing to use safetyzero. You're basically saying that, okay, this function takes a string, but I want to make it faster, so I'm gonna make it speed or safetyzero. That string could basically do any. It's just raw byte. It's basically like C pointers. Like you could treat a string as an integer if you wanted to. Like, you have to be very careful. You're not getting any safety checks at all with safetyzero. So your compiler can totally just corrupt all your memory if it wants.
Yeah, absolutely, and that's something that also that there's this myth that if you make it safetyzero, it's just going to magically get faster or something like that. Yes, you're going to get some
You're going to get some speed improvements, but like the thing that it mostly does is it removes bounds checking on SBCL for array accesses. So if you're concerned about that, do it, but don't do it in a declaim at the top level, and don't even do it at the function level inside a declare. Put it in a locally declare block right around the aref call.
Right. So
you wanna really confine it to like the absolute place that needs it, because that's very dangerous stuff right there.
So, and that's something that we should get into. So when you say locally, you really mean like instead of using declare here, you could just simply do like a let.
Yeah.
Right?
So declare can only be used in certain locations, and like in functions, that one location is directly after the lambda list, like you have there.
Yeah.
But with locally basically creates a new place inside of a function that you can use declarations, and it only applies to that block.
Right. So if instead of doing this, I mean, this is going to be nonsense because I think it'll be equivalent to just doing a declare. But I could certainly wrap this guy and make this a locally block, right? And then
I'm not sure if that would work.
And then
I'm not sure if the declare right after the lambda list has to be a declare or not. I'm not sure. I've never tried that because it hasn't made much sense to do that. If you want to try, go for it.
I may as well. This sounds like something that would be pretty useful. Let's see. Just making sure that I got everything good. But for some reason,
I'm not sure. Since it's a symbol, I'm not sure if the compiler will look explicitly for the declare symbol there. So it works. Okay.
So let's see. But it increased the compilation significantly to 53 bytes. Interesting. Oh, because the bounds checking is happening. I mean, there's some additional checks that are happening here before it goes into the locally block. I'm wondering what this guy does. This is not a macro, right? Locally? No, it's not.
No.
I don't think so. Let me do a describe on that guy. There we go. Let's see here. Sequentially evaluates forms in lexical environment where the declarations have effect. If local is a top level form, then there's no top level forms. Okay. All right. If you're, I wouldn't say. I would make the argument that this here that I just created is a ridiculous. It's a contrived example, but it can certainly show you that you can use locally and provide your declarations, and then outside, if you add some additional stuff here, it's what's it? It will not. It will not. Those declarations in that locally block are lexically scoped. So those declarations, once they're out of that scope, are gone. You will not get any sort of optimizations or type information in the next section of the code outside of that locally block. So that code is the only code that's going to have that type information for the lifetime of that function. Okay, so let me just quickly go to some comments that were being made in our live chat here and respond to some of them. Again, we're not talking about macros in this discussion. I will not talk about hygiene and go into a philosophical discussion about hygiene and compare macro systems. That is just not the intent of today's discussion. Honestly, hygiene or not hygiene, I am not an expert on that topic. If I could somehow get David Moon to come and give us a talk on hygiene or some of the other Lisp experts, I think it would be great. But I will not.
Yeah, let's not go there. I think it's a non-issue, like hygiene or not. Like, even if Common Lisp doesn't have hygiene, you have gensim, and like as soon as you become experienced with Lisp, you know that you have to type gensim. Yeah. It's not that big of a deal.
Yeah, exactly. So
it's not.
So that comment there, I'm not gonna even begin to talk about that. The other one, dynamic. So there was a comment about dynamic languages are notorious for holding latent bugs, Common Lisp included. Okay, again, that's another discussion on software engineering. That I mean, there are good practices in any language for software engineering to prevent bugs. Some bugs are going to fall through the cracks. Statically typed languages are notorious for having bugs, even though people say, well, the thing compiled, I mean, compilation means nothing when you're trying to check functionality and making sure that they match requirements. All right, so I can't make a comment on that.
And like, good software design doesn't come from a good language. It comes from, clearly thinking about your designs.
Right. Yeah.
It's basically the opposite of random. I mean, anybody can type a bunch of random code, but if it's disorganized, it's hard to maintain, and then sure, you're going to get bugs.
You're going to get bugs.
Exactly. Think about your problem and sketch out your ideas clearly with good APIs, and that's good software design. Yeah. It has nothing to do with the language at all.
It has nothing to do with the language. So folks who keep saying, "Oh, dynamic languages are notorious for holding latent bugs," static languages have the same problems if you did misdesign. All right, type design is hard. I'm going to just say this up front. Okay, designing your types and designing to match requirements is a difficult thing. It will get you there at a certain point, but Common Lisp or any other languages, there are certain practices that you need to follow in order to adopt a particular language. All right, let's move on. So we talked about declare, proclaim, but there's one more function that we have not talked about, which is the, which honestly I thought was a pretty interestingly titled operator, but it's it does some pretty cool things from reading the documentation on it in the hyperspec. So what does the do? Right? The basically allows you to specify what the return value of a particular form is typed as. So, for example, if we use, and again, I use fixed nums in numerical numerics just because it's easy to come up with some examples here. If we say the fixed num, and we specify a form like adding two integers, and this is straight up from the documentation, right, from the hyperspec. This, if we do a type of this guy, okay, you will see that what is actually returned is the type for a fixed num integer. All right. Now, obviously, folks who are reading this are like, how do you know that that's a fixed num? You gotta go look that up. I didn't know that was a fixed num until I looked up what fixed nums are doing, and it's based on the implementation that you're running this form against. Okay, some ranges on what the valid range for fixed num might be different based on the Lisp implementation. All right.
You can type integer length of most positive fixed num. I think will give you the number of bits.
Integer length.
Yeah.
And then most positive.
No, it's a constant.
Oh, it is a constant. Okay, so plus.
No, it's just a constant without the pluses. The standard doesn't use pluses for their symbols, for their constant symbols.
Oh, they don't even use stars. Okay, cool. Okay.
So 62 bits is the max bit length on SBCL. So that means it uses 2 tagging bits because this is a 64-bit architecture.
Right. So
CCL actually uses 60 bits, so it actually has 4 bits of tagging. So that's important to keep in mind if you're trying to target, the 2 most popular implementations. You need to, take the min of those 2.
So you said CCL uses 4 tag bits and SBCL uses 2 tag bits, right?
Yes.
Okay.
For fixed nums.
I think this is a good point to introduce what a tag bit is, because I don't think we've discussed this for folks who aren't familiar or coming from other languages. I think knowing what this is will at least inform you when you look at some of this information, what it means. So Common Lisp and most Lisp implementations that you have some sort of type information use what's commonly attributed to as a tagged architecture. So a tagged bit is representing, okay, and I may get this completely, I may butcher this, so Michael, correct me if I'm wrong, all right? But my understanding of tag bits are they essentially provide the type information at the machine level, right? So it tells you what type it is in those first 2 bits, in those bits, those assigned bits. When you assign those tag bits, so in the case of CCL, there are more tagged bits, which means more type information could be actually encoded, so to speak, in those
basically.
Bits.
But the thing to realize here is well, for one, there's 2 things to realize. It's not just fixed nums that are tagged. Basically, everything is tagged.
Right.
Floats, especially floats, double floats, because you can't get the full 64 bits out of them. But the second thing to realize is this only applies when you want to get the return value.
Right.
So if you want to store 64-bit numbers inside of an array, you're not going to have any penalty there unless you try to, index into the array to return one of those. Actually, you can store a specialized array of 64-bit integers, and because it's specialized, implementations may tightly pack those arrays. So it's going to be just like a C array or whatever, where you have 64 bits after 64 bits packed tightly in the array. But it's not tagged until you try to fetch it.
Okay, so a question here: are tag bits related to boxing? So,
Yes,
yes,
that's exactly what they are.
that's exactly right. And what does specialized mean in this context? Um,
Specialized. So arrays have this concept of being specialized or not. And what it means to specialize an array is you basically say that your array is a homogeneous typed array that can only store a particular type in it. And depending on the type that you choose, um, like implementations are allowed to basically not specialize certain types, but basically the only thing you can specialize and have it be considered a tightly packed array is numbers and characters. So like floats, integers, uh, and characters, I believe too. But by being specialized, it basically means that your array is highly optimized because the compiler knows the types that are in the array, and that there's no like pointer indirection. Basically, you're actually storing those types directly into the array without, you know, following pointers because they're stored elsewhere in memory or whatever.
they're a real set of values. They're right, is what you're saying. Like you can access when you're accessing something inside an array through an array reference. What you're actually getting is not a pointer to another location in memory. You're actually getting the value that's represented in that location, that's stored in that location.
Yeah, and the standard actually provides a function to test if like implementations are allowed to what is called upgrade an array. So if you create a specialized array of, say, 64-bit integers, like unsigned 64, implementations may or may not packly type that array. And there's a function called upgraded array element type, I believe.
Upgraded. Let me describe this guy.
Which will tell you upgraded array element type. That'll tell you. So, for example, call that on the type like fixed num, just something simple.
Okay.
Quote it.
Yeah.
So quote the symbol fixed num.
Got it. What is it called? Upgraded. That's what I'm looking for. Okay. Fixed num.
So this means that if you create an array with an element type of fixed num, then it will actually be an array with fixed num stored in it. However, if you were to call like some other type, like say complex, T, that is the top type in Common Lisp, which means there's going to be absolutely no type information on that array. It's going to treat it as generic objects that are, behind a pointer.
Which means you are going to be getting, essentially, if you look at the disassembly, all the generic operations. Right? You're stuck with the. I mean, it's the lowest common denominator, right? At that point, if it's going all the way up to the root level, the root.
Try character, just out of curiosity. I believe that's the only other one besides numbers, because they're basically numbers anyway. Yeah. So I don't know any other ones besides numbers and I guess bits, but they're actually numbers too.
So anything above integer, you're basically
any scalar value is basically upgradable on or non-upgradable on SBCL. So by scalar I mean any single number, not a rational, because that's two numbers, or not a complex because that's two numbers, not an array because that's an arbitrary number of numbers or other elements. Basically any single scalar value, I believe SBCL will create a specialized, highly efficient array if you supply the right types to it.
Well, it looks like here integer, though. I guess maybe it's because it's a unassigned integer.
I'm sorry about that. That is correct, because integer is basically any integer, which could be a big number.
Right. In big num, it looks
there's no bound on integer.
right. But, so for fixed nums, we could do that. We'll create a specialized type. Big nums and integers, because there's no potential bound to know, it can the only option it has is to go all the way up to the generalized type, right? Because there's no strict bound on it. Interesting. That's actually very, very cool. If we used unsigned type, right? If I do this, unsigned byte, say 32, it should recognize that and make a specialized array, wouldn't it? Yeah, it does.
Yep.
Okay, perfect. Okay. So if you wanted to create an array for 64-bit integers,
and you could even try unsigned byte 30 or 64,
right.
And that will too, because it's inside of an array.
Right. So in which
it
case,
doesn't have to be boxed.
You can actually then store 64-bit integers this way, right? You can store 60.
Yep.
Okay. There you go. Yeah.
Or float 64. It's double floats.
True. All right. Yeah. Floats or 64-bit integers. Or
it's only when
doubles.
You want to actually return one of those values from a function that it causes a problem, because then it has to be boxed.
Right.
And as soon as it has to be boxed, then you can't optimize that function. Like if you do optimize speed, but you're returning, a 64-bit value, that's going to be a problem. You're not going to get all the optimizations. You're going to get some compiler notes from that.
So you could delay. So would you say then a good practice then is to delay it as far as you can until you really need to, like, say, return it, and then at that point just box it using like a DAW, and then
not sure what you're asking.
So what I'm asking is when you're creating, if you're dealing with 64-bit values, right, and you're going to prevent incurring the cost of boxing the value and then dealing with generic operations, if you late cast it to what you really need to return from a function, then the compiler, and I guess maybe it's dependent upon the compiler, could use that and optimize the crap out of the operations until it really needs to go and box the value and then box it, right?
Yeah, I suppose. I mean, like,
does my question make sense? Basically, it's late. You're declaring the return value, the point where you really need the value to be accessed, the point where you're going to actually do the boxing. But and as long as you don't box it early, the compiler should be able to leverage the fact that it has a specialized array to actually do whatever it needs to do.
Yeah, I mean, for all your intermediary operations, if they're in an array and all those functions are optimized speed 3 or whatever, you're going to get all the benefit. But at the very output of your function, of your program that needs to return, say, a double float or an unsigned byte 64, that function can't be optimized. Well, it can, but it's not going to get all the optimizations because it actually has to cons that number.
Yeah, that's right. Yeah, and once you have to con something, you're essentially.
Remember, we saw up above that anything more than 62 bits for a number is basically stored on the heap.
Yeah, that's right. That's right. That makes sense. All right. So let's talk about how to create custom types, and we're going to be talking about type B. So we've discussed in the past when we were talking through Common Lisp and different ways of creating types. All of these are ways of creating types. Okay, def struct is creating a type. Def class is creating a type. We haven't discussed this one, but define condition when you're creating new custom conditions. You are defining a type. All right, but in addition to all of this, you could create a type that could be a restricted version of an existing type. An example of that is, and you use essentially something called def type in order for you to do this. 1 second, I just need to correct something here in my notes. So, what is def type? Def type takes in essentially a lambda list, all right, and I think the best way to do this is here. It takes the name of the type that you want to create, all right? Let's say the best one that I came up with to illustrate this is counting number, right? Because just nothing more, like actually not even counting number. I'll use hand number, right? This is essentially only the number that you can count on your hands, all right? It's a really dumb example, but it actually purpose is nothing more to illustrate what exactly you're attempting to do. All right, that's all. All right, and you can define this guy and use that as essentially nothing more than an alias to say integer from 0 to 10. Right? Actually, we could make this even a fixed number because it is a pretty small number. Right?
Integer 0 to 10 is a fixed number.
Behind the scenes, we'll convert it, right? Or if I do this, it will get converted into a fixed number, right? If I do this,
no, it won't get converted. That has to be quoted, by the way.
Oh yeah, that's right. I have to keep forgetting that when I do this.
Like integer 0 10 is a subtype of fixed number.
Really? Oh, well, that makes sense, actually. I kind of assumed that that was the case. But let me try this again. Integer 0, 10, fixed number. Okay. That's interesting. So I don't have to explicitly say that this is a fixed num because this is already going to be converted into a fixed num. Okay, cool. All right. So now that we have this type, all right, we can actually leverage this in we can use our existing API to actually go and not this one, sorry. If I do type p 10 and number, you'll see that it will it's already built into our type system. It's registered with the Lisp REPL. We can actually go in and use all the existing functionality to actually go and determine this, to use this. But what uses these are these types? Well, one is obviously to create declarations inside your function, especially if you want to create restricted types. So you can see this in this case. If you pass
when you're done here, I'll show you a really good use for it.
Okay. This is just we're essentially introspecting to make sure that there are valid and invalid numbers. But in addition to that, you can use it in a sense with defining functions that can go on type switches. And I mean, we're kind of getting close to running out of time here for today's session, but I wanted to bring this up because type case and e-type case are very, and those are the functions that you would use to go and look at the type information when you're when you can use it in SBCL to compile at compile time, but it's mostly at runtime information. You'll go look at the type, check the type, and then dispatch based on the type that's being passed in. I'm only introducing it to you guys here right now. We will be discussing it next time on this, just because of the fact that I think that's going to be a bigger discussion on, and I'm guessing that there are going to be questions related to when this is useful. And I wanted to bring in also some other languages in comparison as to why this is a pretty cool thing that's been available since the inception of Common Lisp that I think has been a bit underappreciated in recent years. What is it that you wanted to show, Michael?
It's probably a little bit more involved than the last couple minutes we have, actually, so we can defer that.
If folks have questions, let me know. Otherwise, if there's something that oh, okay, here we go. What are the fields of the return from of type of 10? So the type of operator returns essentially, in this case, a restricted object, right? Here in this case, it's the lower bound of this integer value and the upper bound, which is a 62-bit. That's if you do 2 to the 62. This is what the value is 2 to the 62 is. -1.
Right. An integer is, yeah, like, is an integer also, like, is subtype P integer big num T?
No, big num is of type integer. It's the other way around.
Yeah, the other way around. That's what I meant. Yeah, so, okay. Yeah, what you said is right.
So when you're looking at integers, at least in fixed num values here, right? Yeah, cool. What you're getting is the type and the bounds in which this is a valid member in. All right. You're not just getting that this is of type integer, because there are different ranges of valid values that you can get associated with this. All right. Yes, as far as I know, most positive, if we do most positive fixed num, it is 62 bits. That is what it's equal to. So when you're looking at smaller types, when you know, in fact, I would make this argument, when you know that you want a particular smaller subset of a particular type, and this is a good form of documentation, especially for folks looking at the source code. Making, in my opinion, a type that represents that range and then adding a name to that is golden. It's good. All right. I think that's a great way of actually putting some types into your code. I don't know what your thoughts are on that Michael. But
yeah, sure. I mean, yeah, I wouldn't use arbitrarily restricted type downs for like optimization purposes, because like usually the compiler is optimized for like powers of 2, like 8, 16, 32 bits and stuff like that.
Right.
So if you do like an integer between 4 and 9 or whatever, I mean, you might get worse performance than just like a fixed num. It all depends. Like compiler magic is very black magic-y.
That's a good way of putting it. Are there any other questions?
But for documentation, definitely, yeah. That'll clearly show whoever's reading the code, this can only ever be between this bound and this bound.
Yeah, and it helps. It helps at least when you're reading through code as you're restricting. But like Michael said, don't try to make it so that if you're trying to make a restricted type, especially a restricted integer type, to stay within powers of 2, just so that your compiler doesn't do anything shitty just because of the fact that it's trying to respect the bounds of your type. Just giving you that heads up. Yes, I will mention this one thing, and then we'll call it. And that is for folks who want to read a little bit more on types, but feel that that section 4 of the hyperspec is a bit dense. There is a nice tutorial on types that was an inspiration for this talk that I took notes off of. And that's from the Common Lisp cookbook. I don't believe, but I think also Common Lisp Recipes, E.D. White's book, mentions type annotations, but I don't remember in what chapter. I have to go and look that up. But that's also another.
I actually got it right in my lap. I'll look it up.
I think somewhere it's mentioned about types, but I don't know in what respect it was brought up.
I kind of forgot how long the index was in this. Never mind.
It's a big book. Yeah, it's a really big book. I actually bought the ebook version, and I was like, man, this sucker is. There's a lot of information in this sucker. I need to go and purchase the paper version just because I like being able to skim through various parts of the book at the same time. So next time we're going to go continuing our discussion on the type system, just because we've only kind of scratched the surface, but I think I've given most of you a good, quick very quick overview of what's available that you could use today. Declaim, declare, proclaim, the built-in types. Look in section 4.2.3 to see what available built-in type specifiers are there that you can use at your disposal. Next time we'll be talking about typecase, e-typecase, and how to write some functions that leverages some of that. And it will look an awful lot like, for folks who have been playing around with the language, Golang, but it's not. It's been around 20 years earlier. So thanks a lot for joining us. Oh, and before I forget, just because it was asked, for folks who want to ping me regarding either talks, ideas, or feedback, provide feedback about this, I'm available on the functional programming Slack as Bugram. I'm also available, I think, as Bugram on the Discord server too as well. And I'm usually squatting there, so you could just ping me and ask me questions or provide ideas, or straight up saying you're wrong about this one thing, and I'll correct myself, and I'll make sure that we can continue moving the discussion. I'll see you guys next week.